Hi everyone, my name is Hemant Yadav and I will be presenting our ASRU paper. This paper is in joint collaboration with Erika Cooper, Junichi Yamagishi, Sunena Sitaram, and Rajiv Ratan Shah. The title of the paper is Partial Rank Similarity Minimization Method for Quality MOS Prediction of Unseen Speech Synthesis Systems in Zero-Shot and Semi-Supervised Settings. A typical overview of what we add to the research community is this. If you have some input, which is the audio in our case, and then you have the MOS scores, that is the labels that we want to predict. Then instead of just minimizing the L1 distance, what we do is we try to minimize their partial rank in comparison to everything, in comparison to all other samples in the batch. And also we could extend this comparison if we want to. But since the main comparison that we have is within the batch, that's why the rank matrix that we have is partial. Okay. And to explain our contributions we explain why relative position in the rank order is important to consider when solving the MOS prediction task. This is the task we try to automate. This task simply means that, let's say, if you have n number of TTS systems, then which system is better? So it's a ranking task. That's why the relative position in the rank order is important. And this is what we propose in this paper to use to model the problem and solve it. And we formulate a loss function for this, which we call partial rank similarity loss. Furthermore, we also introduced one algorithm in semi-supervised training, and we empirically demonstrate the effectiveness of our proposed loss function in out-of-domain speech synthesis systems in zero-shot, few-shot, and semi-supervised settings. If I go over the approach, so yeah, let's just read the first sentence and then it will be clear what is the input. So imagine this, you have a list L1, L2, and L3, 1 through 2, where each element represents an absolute MOS value assigned to a different system. Okay, so now you could say that L1 has a score of 1, L2 has a score of 3, and L3 has a score of 2. So we could say that L2 is better than L1 and L3. L3 is better than L1, but worse than L2, and L1 is worse than L2 and L3. And this is what we see if we create this partial rank matrix. What it does is it simply compares everything to everything. And yeah, once you have this, given some input. So now this input could be your ground truth and your predictions. And that's how we formulate the loss. That is, we try to maximize the similarity between them. That's why the loss is called partial rank similarity. And in detail, this is how the loss function looks. For our use case, the value of P is 1 because we only take L1 norm. This is because in previous work, it was found that L1 is better compared to L2 for this task. Furthermore, as I said previously, that you could extend the comparisons far beyond the current batch, and that's what we call extended PRS function, which is simply keeps our dictionary of previous comparisons that we have made, and then we use them for comparisons. That's it. Okay. Yeah, and then but what we have is our BAPMOS algorithm that we use for semi-supervised training. I will come to this later. Let's first see some experiments that we do on our proposed algorithm. Okay, so as you can see, we have a basic L1 loss, and then this paper, which is similar to ours, but different. And then these all are our like the variants that we propose, PRS, and then the extended PRS. And then you have this lambda C. This lambda C is a hyperparameter that we have to choose. And what we find is that in domain, it's like 1 with extended PRS gives us the best results in SRCC for utterance level, and for system level, it gives like very close to other cases. Okay, yeah. Okay, now let's talk on outer domain. So what we find that in outer domain, our with 0.1 gives very good SRCC results. That is the ranking compared to all the other systems. At most gives 0.479, which tries to minimize also the L1 distance, which we do not. And that's why in outer domain system, we get very good results. Same goes for your BC, which is 0.684 to 6.6, and then 431 to 490. So what we see is that our proposed system is able to generalize the rankings better in unseen systems and unseen languages. So this BC and COM are Chinese and Japanese. This ASRU is same language as the training stage, English. So now that you see that in the proposed function is better able to generalize in OOD settings and is very competitive, or you could say almost same as other functions, and sometimes even better. So our proposed function beats the previous state of the art. Okay, now what we do is that, so here we were just using so we were not fine tuning on these different OOD data sets. We were just using their test sets to get the output. But here what we do is we do the fine tuning. So there's few short, and then there's semi-supervised, and then there's this zero shot. That's it. But for this, we use some split from some paper, which is reference on 8. Okay, yeah. And then what we see is that we have, let's say, 0.651, and then we do few short. That is just 10 samples, we get 0.69, which is good. But yeah, and this is like the training one, and this is the fine tuning that we do on this data set. So what we see is that the best model always comes when the stage 1 training is done using our loss function, which is able to learn better generalizable parameters. And for all the settings, we beat everything, which again shows the OOD capabilities of our proposed method. And we also do it for this language, which is Git Kisan. And yeah, we get very, very good results. And one more thing we do is, as I said, so in semi-supervised setting, we have the unlabeled samples, as you can see. So what and the same goes for the few short. Okay, so not for few short, only for semi-supervised. We have some labeled and some unlabeled. It could be we have 0 labeled, we have some labeled, but we have unlabeled. So what we do is we get the pseudo labels for these unlabeled samples, and we were using all of them. But what we do is we get these numbers, 0.778 again. So now what we do is this number of bins is a hyperparameter in this BAP-MOS algorithm. And the moment we just introduce this BAP-MOS algorithm to select not all the samples, but very few, based on some heuristic, we improve the SRCC results again. And as we increase the number of samples, we get even better results. This was not the case earlier, as you can see. If you had 0.136, 0.676, it was getting almost same results. So yeah, all in all, our proposed idea generalizes very well, as we say in the title. That is, the idea is to minimize the partial rank similarity, to do quality MOS predictions of unseen speech synthesis systems in zero shot and semi-supervised setting. And with this, so yeah, I just want to add one more thing. One more thing is this. Should the research community treat MSc and LCC as reliable evaluation metrics? These metrics are based on absolute values, not the relative rank, which should be used for evaluation the MOS prediction task. As we can see, our MSc values are very high, but still we get better SRCC values, better k-tau values. So yeah, the research community should ponder on this question. And with that, I would say thank you so much for listening to the end. And if you have any questions, you could email us. You have the email IDs, and yeah, we will be happy to respond. Thank you, everyone.